Hi, folks, and welcome to the third video in a series of dealing with the second law of thermodynamics. So this one is potentially very powerful for you as an engineer and as a student regarding learning more about the Carnot cycle and how that relates to the second law. So let's see what we've got. I've entitled this video CarnotCycle 101. Try to bring you up to speed as quickly as I can with some details that'll be actionable for you. But first, what we need to, and here's the roadmap of what we're going to do. Want to give you a crash course for any system operating in a cycle. We'll encourage you to start with a sketch, that schematic sketch that I hope you're thinking about. We'll remind you about applying the first law for any cycle. And then quantifying measures of performance. How is a real world cycle, how does it perform? How do we quantify the performance of a cycle? Then we're going to talk about the Carnot cycle. We'll have a quick slide about who was Sadie Carnot in the first place. What is the Carnot cycle? And I'm going to repeat myself a number of times. There are four special processes that describe the Carnot cycle. And we'll relate those four special processes then to how we measure the performance of various Carnot cycles, and then compare how does the Carnot cycle performance compare to other proposed cycles. So that's where we are, and I'm going to try to step you through it as we go. What do these four images have in common? Let me pause just for a little bit so you can eyeball those four images, see if you can identify what's described by those images, and then we'll go from there. All right, now, what they have in common is that all four of those images are all systems, closed systems that are operating in a cycle. Each of them is operating in a cycle. All right, let's start with the easiest one first. Well, this is a refrigerator operating in a refrigeration cycle. Okay. Next easiest, I hope you recognize this is a window air conditioning system. Works on the same cycle as the refrigerator. Okay. Let's move up here, top left. Well, this is an electric power plant. It turns out that this particular power plant is the John Amos power plant just west of Charleston, Charleston, West Virginia. And this is the outside compressor section of a residential heat pump. And so, of course, it's my hope that you've heard of the equipment called a heat pump, and I'll introduce you to how that works if you're not already familiar with it. Okay, so as part of our crash course, want to look at some basics of thermodynamic cycles. I've shown two schematics here. So let's look at the power plant cycle first. What do we see here? Well, we see, for both of these, we see a high temperature heat source reservoir and a low temperature heat sink reservoir. For a power plant, we see some arrows. We see heat flowing in to this black box. Heat flowing into this black box and heat flowing out of the black box. Those are the arrows. We also see net power flowing out of the black box. So three arrows, three directions of energy transfer. Let's look at this one down here, depicting a refrigerator or a heat pump. Notice here the same temperature reservoirs, TH and TL, but the arrows are reversed, and that's communicating that heat is flowing out of the low temperature reservoir into the black box, and heat is flowing, I said that wrong. Heat is flowing out of the low temperature reservoir into the black box, and heat is flowing out of the black box into the high temperature reservoir, and also we're using power. Power is flowing into this black box. So these are the basic schematics. When you start with a sketch and you're dealing with power plants or refrigerators or heat pumps, my recommendation is you always draw one of these that's appropriate for your engineering problem. Okay, so let's look at the basics of a power plant, also known as a heat engine in thermodynamics classes. And I want you to imagine that you're the manager of this big electric power plant. Now, one of these days that could be, you may eventually have that role as being the manager of a monster size electric power plant. Okay. Now, an electric power plant operates in a cycle with water and steam as the working fluid. Okay. And so, as the manager of the plant, what's your objective? What is your objective in managing this plant beyond drawing a salary? Well, your objective in your job is to produce and then sell electric power to consumers who demand this commodity. So it's a good demand for that. It's a good demand for electric power. That's your objective. You want to produce and sell electric power. What does it cost you to run your power plant? Now, you're going to know there's a lot of costs associated with running any business, right? But let's just look at the thermodynamics part. And so what it costs you to run your power plant is the cost of fuel required to operate the plant. The cost of fuel, that's what it costs you to run it. So summary down at the lower part of the slide, objective, produce electric power to sell it. What's the cost? Fuel. That's all you got to know. We're going to move on from that. Now let's look at a refrigerator. You probably have a pretty good familiarity with refrigerators. Okay. A refrigerator operates in a cycle with the refrigerant R134A as the working fluid, phase change substance. Okay. What's the objective of running your refrigerator in your kitchen? What's your objective? Well, your objective is to keep your food and beverages cool inside that box. That's your objective. And you know it costs you something. If you pay your electric bill, it costs you what it costs to purchase electric power. You're one of those consumers from the power plant, right? But you've got to pay to buy that electric power to run your fridge. Okay. Summary. Objective is the cooling effect, heat transfer in your fridge. That's the cooling effect. And what it costs you is electric power. Pretty easy. Window air conditioning unit or air conditioner in general. Now, it's not like you need an air conditioner to live, but really for those of us here in the comfort of the USA, we sort of depend on air conditioners for our comfort, don't we? The air conditioner also operates in a cycle with refrigerant R134A, phase change substance. Okay. What's the objective of running your air conditioning unit? The objective of running your AC is to keep yourself cool. That's your objective. Okay. And what does it cost you to run an air conditioner? Well, there's that. There's the power cord right there. You have to buy electric power. Now let's look at my schematic. I've added a little stick figure in the schematic. This is you. Here's you in the low temperature reservoir. This is kind of like your room, the space in your apartment or your home. And the objective of this air conditioner is to pull heat away from the room and you, okay, and transfer it to the outside at the expense of buying electric power to make that happen. Okay. Objective, cooling effect. Here's that stick figure. That's you. Okay. Cost, electric power. And now I'm hoping that you're seeing the repetition of where we're headed. I keep talking about what's the objective, what's the cost, what's the objective, what's the cost. You might not have quite so much familiarity with a heat pump. Okay. But you might be familiar with a residential heat pump. Heat pump operates in a cycle with a refrigerant. The refrigerant probably R134A. Okay. Now, what's the objective of running a heat pump? A little different than an air conditioner. Okay. The objective is to heat the inside of your house, not remove heat from the inside of your house. And so look how I've moved the stick figure up into the high temperature reservoir. So the objective of the heat pump is to move heat into the high temperature heat source from a lower temperature heat source, but it takes electric power to run the compressor section of this heat pump. So you've got power that you've got to buy. So there you get objective, heating the inside of your house, the cost, buying the electric power. Objective, home heating effect, cost, electric power. Look how similar that is. Okay, now I want to say a few words about these schematic sketches. Take a couple of minutes to look at the right-hand side and the left-hand side sketches. Find out where they're similar and where are they different, okay? They are different. As you look, how are they similar? How are they different? I see some dots on the right-hand side here. That's really the only difference of each of these is a heat engine. I'm making some net work or net power. So the difference is the dots over top of my heats and works over here. And so in your textbook situation, you're typically looking at pistons and cylinders, and you're analyzing one single cycle. In other words, this black box goes through one single cycle, and an example would be process 1 to 2 to 3 to 4, and then back to 1. 1, 2, 3, 4, 1. Went through one cycle, you did your homework, and the results you got in terms of heat and work, the units were in kilojoules or BTUs. Okay. Now and that's perfectly valid. Those are good things to be able to analyze. Then we move into the engineering world where we're operating things, where we're running a power plant, or we're running a fridge or a heat pump or an air conditioner. In this case, we're running a power plant, okay? Power plants run 24/7. They don't just run through one cycle, do they? They run 24/7 continuously. Thank goodness. So therefore, that's why we have Q dot, the rate at which heat is added to the plant, okay? W dot, the rate at which net power is produced. And Q dot L, the rate at which heat is rejected to a low temperature reservoir, usually the surroundings. Okay, and so similarities, TH and TL, heat reservoirs, okay? Both are systems operating in a cycle. Over here on the left, one single cycle of operation with units of kilojoules. Over on here, running 24/7, steady state, steady flow at a constant rate, units, kilowatts, or BTUs per hour, or in terms of power output, horsepower. I hope that makes you feel a little more comfortable going from textbook to real world and back and forth. Both are extremely important. Both are very valid. Okay. In our crash course, let's remember the definition of the first law of thermodynamics for any system operating in a cycle. And let's do both. The closed system, where you're going through one single cycle, 1, 2, 3, 4, 1. And then also the power plant, where you're operating continuously at a certain rate. Okay, closed system, went through one cycle. The cyclic integral of heat equals the cyclic integral of work. That's the statement of the first law, system operating a cycle. So therefore, now when you look at your schematic, what's the cyclic integral of heat in? The cyclic integral of heat in, I see an error. Here's something going in, and here's something going out. So the cyclic integral, as you study all surfaces of your black box, I've got plus QH minus QL. That's the cyclic integral of heat in. The cyclic integral of work out, I've only seen one arrow that's associated with work, and there it is. And so the cyclic integral of work out is simply W net. So you might say, well, that's a formula. Well, that's where you get the formula, is with your eyes doing the cyclic integral of heat, cyclic integral of work, QH minus QL equals W net. Now for the rate version, we're running 24/7. All I did here is put dots over top of the Q. The cyclic integral of heat transfer rate in equals the cyclic integral of of work power out. So therefore, pretty straightforward. Q dot H minus Q dot L equals W dot net. So these are statements of the first law, energy balance for systems operating in a cycle. Very important that you get that more than just treating it as a formula. Okay. Now we're going to get into how do we quantify the performance of any power plant, any heat engine. Okay. And what we do is we define the thermal efficiency of a power plant as eta thermal, eta, Greek letter eta. This is not letter N. It is Greek letter eta, eta thermal, thermal efficiency. And here's the way that my professors were so good at repeating this over and over that it finally absorbed it. It took me a while to absorb it, but I finally absorbed it. The thermal efficiency is defined in words as energy sought over the energy that costs. The objective divided by what you got to pay for. All right. So again, now I hope that I've set up the thing. I hope I've given you enough examples where you say, for a power plant, energy sought, W dot net, net power output. I'm going to sell that. Okay. What cost me? What cost me to run the power plant? Q dot H, the heat added. Okay, so I think I can remember that. I think I can remember it now. Energy sought over the energy that costs. I can remember words easier. I can remember a formula, quickly derive the formula, and then I'll apply the first law to the formula. W dot net equals Q dot H minus Q dot L from the previous slide. Okay, so I don't know. Each of our minds work uniquely and differently. So whatever works for you, I want that to work for you. Don't feel obligated to do it my way. However, I found that if I can remember some words, and then I can generate this formula, and then I remember what's the first law? What's the first law for system operating a cycle? W dot is Q dot H minus Q dot L. That's the way I got it. All right. So let's move on. And so energy that, back to the schematic, the energy that costs, Q dot H, the energy sought, W dot net. All right. I declare you an expert in thermal efficiency analysis of power plants. Let's move on to a refrigerator or an air conditioner. Both of these pieces of equipment work in the same thermodynamic cycle. And the way we define the performance of a refrigerator or an air conditioner is with it's Greek letter beta, beta refrigerator, beta refrigerator, beta. So Greek letter beta. That's not letter B. Greek letter beta. Okay. In a lot of times in the world, you don't see beta, but you will see COP for coefficient of performance. So these are synonyms. Beta, refrigerant, COP, refrigerant. Those are synonyms, all right? Now, here's what I want to suggest. Instead of trying to force yourself to memorize a formula on a formula sheet, go with this. Beta for refrigerators is the energy sought over the energy that costs. And so for the schematic or refrigerator, what are we seeking? What's our objective for the refrigerator? Well, we're trying to cool a space in the refrigerator, the refrigeration effect. So our energy sought is Q dot L for this case. What costs us for this case? We've got to buy electric power to run our refrigerator. So the energy that costs us is W dot net. So now I hope you're seeing the drill. Then we're going to apply the first law for a system operating a cycle. Coefficient of performance for a refrigerator is Q dot L divided by Q dot H minus Q dot L, which is equivalent to W dot net. Got it? Now we're moving along to a heat pump. That heat pump, oh, in my schematic, look what I've done in the schematic here. I've drawn a little stick figure. That's you trying to be heated up in the winter in your house or in your apartment. That there you are. Okay. So for a heat pump, the coefficient of performance is now, it's not beta anymore in your textbook. So I want to be consistent with your textbook. It's Greek letter gamma. That's Greek letter gamma. That's not Y. That's not letter Y. Okay. Gamma of the heat pump, gamma of the heat pump, is the energy sought over the energy that costs. Okay. Look at your schematic. What are we seeking? We're seeking to stay warm. Q dot H. Okay. Energy that costs us. We've got to buy electric power to run the compressor. Energy that costs here. Okay. W dot net. So again, well, we're going to apply the first law. So gamma for the heat pump, coefficient of performance for the heat pump, is Q dot H divided by Q dot H minus Q dot L, which is in fact W dot net. Okay, it's my hope that these things fall into place for you. And now this is a summary of the previous 3 slides. Power cycle, thermal efficiency is the performance measure. All 3 of these, power cycle, refrigeration cycle, also air conditioner, and heat pump, all 3 of these, the measure of performance is described by energy sought over the energy that costs. Okay. You got to commit to memory. Power cycle is Greek letter eta for efficiency. Refrigeration cycle, that's coefficient of performance, beta. Okay. And gamma, the heat pump coefficient of performance. Okay. And let's see. All right, that's probably the best. And then it's a matter in your head. You see, I've drawn a little icon of your head. Little icon is you should be able to commit these fundamentals to your memory and get them learned, not necessarily rely on a formula sheet to write all this stuff out. Okay, so here's the big conclusion. The measure of performance for any system operating in a cycle is given by the energy sought over the energy that costs. And so you should be able to figure this out without using a formula sheet. You ought to be able to get to your formula quickly by pulling it out of your head. Measure performance, energy sought over energy that costs. So that's the end of the crash course. Now, we're moving on to the Carnot cycle. So this Carnot cycle is a very special cycle, but it's also a system operating in a cycle. And what I'm going to try to do in the next few minutes is talking about this black box schematic where we're going through one single cycle. Let's say it's a piston and cylinder going through one single cycle, 1, 2, 3, 4, 1. And just to give you, this is what a Carnot cycle looks like on a PV diagram. We're gonna beat this to death. So you don't need to memorize this. We're going to really talk about this in detail. Who was Sadie Carnot in the first place? And so I went to Wikipedia to refresh my memory on some things that my favorite thermo professor talked about in class, but here's some neat facts. So Sadie Carnot was a French person. He was a mechanical engineer in the French army, born in 1796 and died in 1832. Okay. And so he was this was heat engine, turning heat into work was a new technology in 1800, a brand new technology. Okay. And anyway, this guy must have been extraordinarily sharp and extraordinarily good student and an engineer, because at age 27, in 1824, at age 27, he proposed a special type of cycle that was fully reversible. In other words, it was a cycle that had no irreversibilities in it, no friction, no unrestrained expansion, no heat transfer across a finite temperature difference, and those other things that we talked about of the 7 things that make processes irreversible. But in particular, no unrestrained expansion, no heat transfer across a finite difference in temperature, and no friction. All right. It turns out that this was so groundbreaking at the time that this cycle, after his death, was called the Carnot cycle in his honor. And if you've had time to browse this Wikipedia write-up, you'll see that he came before Clausius. You've heard of the Clausius statement of the second law, Clausius inequality, and Lord Kelvin. the Kelvin-Planck statement. Okay, he came before these guys and helped further the understanding of the second law of thermodynamics. So that's who Sadi Carnot was. And now we're going to talk about what is the Carnot cycle. A Carnot cycle represents a system operating in 4 specific process reversible processes, 4 reversible processes. Okay. And what it does is this cycle that he proposed exhibits the best possible achievable thermal efficiency, energy sought over the energy that costs. And of course, and then the other thing is recognized with our schematics, we're operating between 2 temperature reservoirs, TH, T high, and in my world, TL. The book calls this T sub C or T cold. I think you're going to be able to I'm going to stick with TL because it's the way I learned it. I think you're going to be able to deal with the difference, the similarity of TL and TC. Now, in Sadi Carnot's approach and his reasoning and his thinking and his studying, his thesis was that the heat transfer QH divided by QL, the ratio of those 2 heat transfers exactly equaled the ratio of absolute temperatures of the 2 temperature reservoirs, TH over TL, as long as you recognize these 2 temperatures are in absolute temperature. So that's the key to his special cycle. QH over QL exactly equals TH over TL. So that holds for the Carnot cycle only. All right. I need you to get familiar with what the Carnot cycle processes are. So this is a little more than, I really hope that you can commit these 4 processes into your memory because it will benefit you on tests, quizzes, and in your engineering practice. So I do want to describe each one of these as we move ahead, other than just saying, well, I think I got it. It's maximum possible thermal efficiency. So I've got it. I'm going to move on. Let's look at this. So this is one of the situations where we're going through one single cycle. Units will be kilojoules or BTUs. Process 1 to 2, first 1 to 2. In the Carnot cycle, it's reversible adiabatic compression, where we're starting in a certain specific volume, we're decreasing it, and we're going up in pressure. Reversible and adiabatic. Reversible, no friction, no unrestrained expansion. Adiabatic, no heat transfer. Reversible adiabatic compression. 2 to 3. Reversible isothermal heat addition. Now, you got to think about how do you add heat when the temperature doesn't change? I'm going to suggest that you have had some homework problems already. I'm not going to remind you exactly what they are, but you have had some homework problems where you have added heat to a piston and cylinder and the internal energy went up, work was done, okay? But the temperature inside the piston and cylinder didn't change. If you do a little thinking, you're going to be able to think about a homework problem where that was the case. Okay, so I'm going to process 2 to 3. Reversible, constant temperature, heat addition. Process 3 to 4. Reversible and adiabatic, that's no heat transfer, expansion. Reversible and adiabatic expansion, okay? Adiabatic, no heat transfer. And then finally, to get back to state 1, we've got a heat rejection process in which we're rejecting heat at constant temperature. It's a little harder to visualize, but I'm going to suggest that there have been a couple of homework problems where we have rejected heat from a substance inside a piston and cylinder at constant temperature, okay, to get back to where we are. So in other words, the pressure's going up, the volume's going down, and that's reversible isothermal heat rejection, okay. One thing quickly for you to notice on this, so that is the special 4 processes associated with the Carnot cycle, okay. How about the work for each of these processes? I wish there was someone live where we could go back and forth, and I'm sorry there's not. But remember, for a piston and cylinder closed system, what's the visualization of work? Visualization of work on a PV diagram. It's the area under the curve. And so do you see for each of these processes, each on this Carnot cycle, there's work involved for each of these 4 processes. Again, something to keep in the back of your mind. Okay, and so here's our next slide is trying to help you get this into your head. Link these 4 special processes with the block diagram that describes the heat engine. So trying to link this visualization with this PV diagram. And so in the red arrows, I said, well, look, here's QH. Well, let's see, where is QH? That's heat addition at constant temperature. That's process 2 to 3. Okay. Next is the net work. Well, the net work, if you've worked with me a little bit, remember that you can visualize the net work for system operating in a cycle as the enclosed area of the cycle. And for this cycle, we're going clockwise. And so the net work is a positive number area enclosed in the cycle. And then finally, reversible isothermal heat rejection. Well, here's QL, and that's process 4 to 1, reversible isothermal heat rejection. And so it's my hope that the slide is helping you link the PV diagram to the schematic. And this is something that took me forever to link in my head. Okay. So if you're having trouble with it now, don't feel bad. You just got to study on it. You got to practice with your homeworks, and it'll come to you. Okay. I'm not going to spend much time on this slide because you see that now I'm using an ideal gas contained in the piston cylinder as the example. And so let's look at process shape details if you've got an ideal gas inside your piston and cylinder. Let's start with process 2 to 3, isothermal heat addition at constant TH. Well, I've got an ideal gas. PV is equal to RT. The right-hand side is constant for constant temperature, isn't it? So in other words, PV equals constant for 2 to 3. That's a hyperbola. PV equals constant. That's right out of high school. Okay. Process 3 to 4, reversible adiabatic expansion. It turns out, and we don't have time to derive it here, it turns out that for a reversible adiabatic process with an ideal gas with constant specific heat, one can show that PV to the K power is constant. So this is like a steep hyperbola, steeper than a regular hyperbola because you got V to the K. All right. 4 to 1, isothermal process, same observation. PV is equal to RT. And so, gosh, the right-hand side is a constant. In this case, R times T low, as long as you've got T low in absolute temperature. So PV is constant. So process 4 to 1 is a hyperbola. And then just to finish off, process 1 to 2, the compression process, reversible and adiabatic. And we can show that PV to the K is constant for an ideal gas with constant specific heat. And remember that K is simply the ratio of CP over CV. Okay, so I'm blazing through that. You might come back to this at a later time if you want to download the static PowerPoint of this video. Okay, this is so important that I want to devote a slide to it. This is a key point that you might not have covered enough in your class. It's a matter of synonyms. A reversible and adiabatic process is called an isentropic process. You must commit that to memory for success in quizzes and tests. A reversible adiabatic process, any process which is reversible and adiabatic, not either or, but and, reversible, no friction, no unrestrained expansion, and adiabatic, no heat transfer, okay? is called an isentropic process, constant entropy process. Adiabatic means fully insulated. Adiabatic means fully insulated. Very important slide. Word count is low. Okay. Visual is high. Okay. And that's why I've made it pretty important. This is a key for you to know. Okay, so let's visualize W net for a Carnot cycle on the PV diagram. We've already touched on this. The shaded area contained within the cycle is the visualization of W net. And notice here that if we go through, let's see, process 1 to 2, there's work involved, but it's going to be negative, isn't it? Because you're integrating from right to left. 2 to 3, work is involved. You're integrating from left to right. Work is going to be positive. 3 to 4, you're integrating left to right. Work is positive. Process 4 to 1, work is involved. Area under the curve. Okay. And you're integrating right to left. Work will be negative. And you add all those up, you're going to get a positive number. You're going clockwise within the cycle. It all fits together. All this really fits together. You're running around clockwise in the cycle. W net, you add all 4 of those works together, you get a positive number. And that's the beauty of the Carnot cycle. And that was the genius of Sadie Carnot. I'll have to tell you, when I was a student, I figured if you added all those works up, they'd cancel each other out. And boy, was I wrong. It turns out that the Carnot cycle is a prominent feature on the Pi Tau Sigma honorary mechanical engineering fraternity key. And so I've shown a screenshot of both. Here's the PV diagram, and here's a screenshot of the fraternity key of Pi Tau Sigma that's associated with mechanical engineering students. And so I'd recommend you, if you're interested, to learn more about that. Okay. It is an honorary fraternity. It's not a social fraternity. And I think Dr. Scott Huxtable is the faculty advisor for Pi Tau Sigma. So I try to chase you to Dr. Huxtable to learn more about this honorary fraternity. All right, now back to thermo. How would you visualize the Carnot cycle on a TS diagram? And this is where there's no way you could have memorized all 4 of those processes in a matter of minutes. You got to study on this. But so I'm going to help you show that, well, here's the PV diagram we've been beating to death. How can we create a temperature entropy diagram that's the same cycle? Well, let's go through process 1 to 2, 2 to 3, 3 to 4, 4 to 1. Process 1 to 2, reversible and adiabatic compression. Okay, reversible and adiabatic, that means isentropic. That's constant entropy. And so process 1 to 2 must be a vertical line on the TS diagram, constant entropy. Okay. Process 2 to 3, reversible isothermal heat addition at TH. Wow, it discloses what it looks like. Isothermal constant temperature at TH. It's a horizontal line at TH. Y equals TH. Okay. 3 to 4. 3 to 4 is a reversible adiabatic expansion. Well, reversible adiabatic, that's isentropic. 3 to 4 is going to be a vertical line. Isentropic, constant entropy. And then 4 to 1, reversible isothermal heat rejection at TL. The words give it away, isothermal. It's a horizontal line, and it's located at Y equals TL. And I say, here's the textbook calls it TC. I copied and pasted out of the book. And so I'm calling it TL, book calls it TC. Okay. So what's the takeaway here? The Carnot cycle on a TS diagram is a rectangle. Put that in your memory banks. Carnot cycle, TS diagram is a rectangle. Crazy looking thing on a PV diagram. Rectangle, easy looking thing on a TS diagram. Now I'm going to walk you through visualizing Carnot cycle QH QL and W net, and how you visualize those with your eyes on a TS diagram. And here's how you figure it out. Okay. I think in my my second law statements video, I introduced this out of the textbook. The integral, well, from any state to any state, it says 1 to 2. That's just the example. It could be 2 to 3, 3 to 4, 4 to 1, et cetera, et cetera. The integral of TDS equals Q for that process. The heat transfer is the area under the curve of the integral of TDS. That's what we're going to work on. So we're going to visualize QH with this integral vision. Then we're going to look at QL with this integral vision, and then we're going to make some conclusions on W net. Okay, QH, the integral of TDS is equal to the heat added for that process 2 to 3. Okay, so we're looking at process 2 to 3, which is reversible isothermal heat addition at TH. Okay, the integral of TDS, do you see it with your eyes? That's the area under the curve from 2 to 3. And so it's a rectangle that goes from the 2 to 3 line all the way down to absolute 0. So that red rectangle is the visualization of QH, area 2, 3, A, B, 2. Okay, there is the visualization of the heat added, QH. Let's now go to QL. Okay, same idea, integral of TDS for a reversible process. That's the heat transfer, all right? Well, now we're going process 4 to 1, reversible isothermal heat rejection. So we're going from 4 to 1. We're going right to left. We can see the area under the curve. And since we're going right to left, it's going to be a negative value. See the area under the curve in the blue? Okay. So area 4 to 1 to B to A to 4. So trying to trace that out. Okay. There's QL. It's going to be a negative number. Okay. So the heat added is a negative number, QL, like maybe 5 kilojoules or something like that. Okay, so there's our visualization of QL. Okay, now we go back to our first law, okay, and we write the first law for any system operating in a cycle. I didn't even put this on the slide because you've got this in your head now. QH minus QL equals W net. So by subtraction, we'll go back 2 slides. Here was QH. Here was QL. QH minus QL equals W net. So W net is the area enclosed in the cycle on the TS diagram. What a coincidence. So we've got a visualization of W net on our TS diagram, and we've got a visualization of W net on our PV diagram. That's very cool. Okay. W net visualization, okay. Clockwise and clockwise. Look, we're going clockwise. We're making work. W net is greater than 0. Over here, same conclusion. Perfectly, everything's consistent with one another. We can also visualize thermal efficiency for the Carnot cycle on the TS diagram. The energy sought over the energy that costs. The energy sought, W net, the crosshatched area. The energy that costs, the red area. So now you've got a visualization of, it's a ratio of 2 rectangles. It's pretty cool, okay? So that's a neat thing to visualize. And also, it turns out that the thermal efficiency for the Carnot cycle, you can show that. It's simply going to be equal to TH minus TL divided by TH. Okay. Energy sought. Remember, a few slides ago, I said Sadie Carnot showed that QH over QL equal TH over TL, as long as you're using absolute temperatures. So you can do the algebra, and so you could start with thermal efficiency Carnot as QH minus QL over QH, true for any cycle. and use that algebraic relationship to show that TH minus TL divided by TH describes the Carnot thermal efficiency. Okay. Cool. So I spent a lot of time dissecting the Carnot cycle because it is my hope. I hope that it's worth your time to go through that. And you might want to even replay it from time to time. But that's the detail level that you need to get familiar with on the Carnot cycle. Okay, so what? So what? What can the Carnot cycle do for me? What can it do for me as an engineer? What can it do for me as a student? What's in it for me? That is a reasonable thing to ask. And I'm going to try to answer that. Okay. Let's say you're that power plant manager. Okay. Power plant manager, how does this apply? It's heat engine. Okay. What are the fundamentals that apply to any cycle in the world, not just Carnot cycle? The thermal efficiency is the energy sought over the energy that costs, QH minus QL over QH, W net over QH. I hope you got that in your head. Now, for the Carnot cycle represents the maximum possible thermal efficiency that can be achieved. So here I put eta thermal Carnot equals eta thermal max. So that's equivalent equals TH minus TL over TH. And so this is what's in it for you. This gives you a powerful tool for quantifying the best possible performance of any available power plant operating between TH and TL. This is the best thermal efficiency that you could possibly achieve. And that was Sadie Carnot's humongous contribution to the world. Okay, that's big. All right, that's what the Carnot cycle can do for me if you're a power plant manager. What if you're just in the refrigerator business, or if you just use a refrigerator and you're interested in the performance of your refrigerator? For any refrigerator, beta, the coefficient of performance, is going to be the energy sought over the energy it costs, QL, refrigeration effect, divided by what you got to pay for, W net, or QL over QH minus QL. So therefore, the Carnot coefficient of performance is going to be the maximum possible TL over TH minus TL. Again, you use that algebraic identity that applies only to a Carnot cycle, and you get this result. And so the best you can do in terms of coefficient of performance, typically a coefficient of performance is a number greater than 1. And efficiency, let's go back a slide. And efficiency for a power plant is always a number less than 1, and that's why we call it efficiency. This is always, do you see how this has got to be a number less than 1? So if QH is any number and QL is some number, this is always going to be a number less than 100% thermal efficiency. Now, over here, you can do the math and you can satisfy yourself that this is nearly always going to be a number bigger than 1. Okay, so if you get a coefficient of performance that's a fraction, you've done something wrong. Okay, I think you can also answer it on the Carnot side as well. Powerful tool for quantifying the best possible performance of a refrigerator. You can put a bound on this. Not anything is possible. Same thing for a heat pump. So remember the heat pump. Now you see the repetition here. It looks like I do see that I've got a mistake here. That's got to be gamma. This should be gamma heat pump, gamma Carnot, not beta. Okay, to be consistent with the book. Some other textbooks use beta. That's why I got goofed up here. But for a heat pump, energy sought over the energy that costs, well, the energy sought for a heat pump is the heating effect, QH. Energy that costs, W net. We use the first law, so QH over QH minus QL for any heat pump cycle is the coefficient of performance. But then for the Carnot cycle, you use the algebra to show that the best possible coefficient of performance for a heat pump is TH divided by TH minus TL. Now, imagine how tough it would be if you had to write all these formulas down on a sheet. You got to get some of this stuff up in your head. Okay, so you might say, you've spent an awful lot of time here. Time's a wasting. Why are you repeating Carnot cycle details over and over and over? And it makes me feel like Bart Simpson a little bit. And the reason is it's important that you get the big picture of this in your head. And so this stuff is not trivial. It is not easy. It's not easy. So it's not trivial. And I've been repeating myself a lot to try to help you get these concepts into your head and not depend on a formula sheet quite so much. Okay, so let's talk about some summary statements about the Carnot cycle. And this can help with homework problems. I'm going to read these three statements. If the measure of performance, the measure of performance, so it's either thermal efficiency or coefficient of performance for a refrigerator or coefficient of performance for a heat pump. If the measure of performance of any cycle, if it exactly equals the Carnot measure of performance, then the cycle is not only is it possible, but it is reversible. Possible and reversible. In other words, it's like a Carnot cycle. It's equivalent to a Carnot cycle. Possible and reversible. Now, next statement. If the measure of performance of a cycle is less than the Carnot measure of performance, if it's not quite as good as Carnot, then the cycle is possible and it's irreversible. There's something going on in the cycle that makes it irreversible. For example, heat transfer across a finite temperature difference. That clearly makes a cycle irreversible. Any kind of heat transfer across a finite delta T, any kind of friction, any kind of unrestrained expansion. All those would be examples of things that make a cycle irreversible. But if the performance is worse than Carnot, it's still possible. Now, finally, there's going to be people that propose all kind of good ideas to you. So it says, if the measure of performance of any proposed cycle is bigger than the Carnot measure of performance, so in other words, if a proposed power plant has a thermal efficiency greater than the Carnot cycle, then the proposed process cycle is impossible. And there's no getting around it. It is flat out impossible. So no amount of wishing or hoping or positive thinking will make that proposed cycle possible. Okay, so we have reached the end of CarnotCycle 101. So we covered a huge amount of material. We repeated a good bit. Okay. I'll need to go back and correct one of my slides for coefficient of performance for a heat pump. Okay. But here's the recap. The block diagram, that schematic block diagram, is a powerful method for describing commonly used cycles in the real world. So, for example, the block diagram can be used to describe a power plant, also known as a heat engine, for a refrigerator or air conditioner, or a heat pump used for home heating. Okay. Various measures of performance for cycles can be determined by the energy sought over the energy that costs. So all of these categories of real world equipment, the performance can be described by the energy sought over the energy that costs. And I owe that to my first thermo professor, who was a chemist, and he harped on that. We can describe the performance of real equipment with words, and then we can derive the formulas from those words as long as we use some common sense. Okay. Finally, the Carnot cycle is the best possible, it's fully reversible, the best possible method for cycle energy conversion efficiency operating between TH and TL. So you can operate as a heat engine, or you can operate as a refrigeration cycle or heat pump cycle between two temperature reservoirs, and that would be considered energy conversion from heat to work or work to heat. And that's the recap of this. So there you are, CarnotCycle 101. Don't hesitate to ask questions in class. Don't hesitate to join online and ask questions online. But this is really, really a powerful part of your thermodynamics course and can be a powerful part of your engineering skills once you get out of college or university and get into engineering practice.